Today we're going to continue our discussion in section 3.1 where we've talked about this idea of derivative, and we're going to look at being able to find the slope of tangent lines and horizontal tangent lines and different things that we can do with this tangent line at this point in time. So the first question I'm going to ask is, what do we know about a horizontal tangent line? So what does a horizontal tangent line look like? What are some characteristics? What's the graph going to look like? So I like to go ahead and start with a graph. Maybe we have a nice cubic function here. And we want a horizontal tangent line. So remember, to be tangent, it's going to touch it at one point. To be horizontal, we have a slope of 0. So we see, or I see, 2 points in which this occurs. We're going to see it at the top here, where we have a horizontal line that's going to go just at that point, that top point, the very highest point. And we're going to see a point down here where we see on the lowest point, we see that we're going to have a horizontal tangent line as well. Not critical at this point, however, later on, these points are going to be extremely important to us. We actually call them critical points of our graph when we get into being able to graph a function without the use of a calculator. You'll enjoy that one. So, what are we going to ask you to do? Well, what do we know about this horizontal tangent line? This horizontal tangent line has a slope of 0. And this one does as well. So if we ask you to find points where we have a horizontal tangent line, we're really asking you to find the slope when it's 0. Well, what is going to be the slope? Where do we find the slope of this curve? And that's going to come from our derivative. So we're going to find the derivative, we're going to set it equal to 0, and we're going to solve for x. Sounds simple enough, right? So let's go ahead and tackle one and see what happens. So here we're going to determine the points on the graph of the function f of x equals x to the third minus 3x squared, where the tangent line is horizontal. Again, a couple of things that we're going to see. We want to see these words tangent line. That tangent line is telling us derivative, and then horizontal, we know that that derivative is going to equal 0. So the derivative here is going to be 3x squared. Derivative of negative 3x squared is negative 6x. So we get the function or the derivative of negative or positive 3x squared minus 6x. We're going to go ahead and set that equal to 0. We should see that we have a quadratic. To solve a quadratic, it has to be equal to 0. Once it's equal to 0, we can go ahead and factor if we can. In this case, we have a GCF, which is 3x. We end up with x minus 2. That's going to equal 0. We're now going to set each of these parts equal to 0. So if you recall, if we have two things multiplied together to give us 0, then we know that one or both or either of these two pieces has to equal 0 as well. So we go ahead and solve. Divide by the 3, we get 0 here, add 2, we end up with 2. So this gives us the x values. Notice in our problem it asks us to determine the points on the graph. So not just asking where x, if it asks where on the graph it is, well, at x equals 0 and 2, that's where it's occurring, but it's actually asking for the points. In order to have a point, we need an x value and a y value. So we're going to take this x value, we're interested in the points of this function. So we're going to take the x equals 0 and plug it in to the original function. So we want to find f of 0. In this case, f of 0, we have 0 to the third minus 3 times 0, which gives us 0. Likewise, we're going to find f of 2 to find the y value in this case. So we end up with 2, plug it in, we end up with 8 minus, plugging in 2, we get 3 times 4, which is 12. 8 minus 12 gives us negative 4. So we're going to have horizontal tangent lines at 0, 0, and 2, negative 4. In this example, as a kind of a big example, a big problem, it's asking us to determine the points on a graph of the function f of x equals 2/3 x to the third plus x squared minus 12x plus 6, where the derivative equals negative 12, 0, and 12. So we have 3 parts that we're going to do here. So the first thing we're going to do is find f prime of x. Derivative here is going to be, multiply the 3 there, we end up with 2x squared plus 2x minus 12. To do part A, we're knowing that derivative equals negative 12. So again, we have a quadratic. We want a quadratic equal to 0 when we go ahead and solve it. So we're going to add that 12 over. And nicely, what happens is that the 12s cancel each other, so we just get 2x squared plus 2x equals 0. We can factor out a 2x, so we get x plus 1 equal to 0. Again, we're going to set each of those equal to 0. And we end up with x equals 0 and x equals negative 1. Again, we want to know the points, so we want an x and a y value for each one of these. We're going to plug 0 into the original. That's kind of nice. Plugging in 0, we end up with 6. Plugging in negative 1, a little more complicated. If I plug in negative 1 to the third is negative 1, times 2/3 gives me negative 2/3. To that, we're going to add negative 1 squared, which is 1. Negative 1 times 12. Negative 12 gives us a positive 12 plus 6. Again, this is f of negative 1. Adding those together, we have 12 and 1. And 3 is 18, 19. So then we're going to add negative 2/3, so we get 18 and 1/3. Again, you can put that in a mixed number, in proper fraction if you want. It really doesn't matter to me. We can go on to part B. It's asking when f prime of x equals 0. So this is an interesting one. This is actually the horizontal tangent line, if you recall from the previous example, when our slope was equal to 0. So we've already found our slope. So we can go ahead and take our 2x squared plus 2x minus 12, set that equal to 0. We can go ahead and factor this since we're equal to 0. So we get x squared plus x minus 6 equal to 0. We can continue to factor that trinomial. We get x plus 3 and x minus 2 equal to 0. Set each of those parts equal to 0. We get x equals negative 3 and x equals 2. So we can take those two values, again, plug them in to the original function. So we find f of negative 3 and we find f of 2. It might be a nice thing here, since we can use our calculator. I'll go ahead and show you how we can do that fairly quickly, especially since we have a lot of these to do. So I would go ahead and do my y equals, clear everything that's in there, obviously. We have 2/3 x to the third plus x squared minus 12x plus 6. So we put that into our y equals. And then we can do a second table setup or second window. And on our independent value, we want to ask. So this is going to allow us to go into our table and ask for the value that we want. So since we're already on ask, if you weren't on ask, you could go down and then go over and hit enter on that. So here I'm going to do second graph, or my table. And here I can go ahead and just type in a number, so negative 3. And that's going to pop up what that y value is. So negative 333 is a point. Here we're going to plug in 2, and I get negative 8.667. Again, if you've worked with me before, we know 3 decimal places is what we're looking for. So you can round it to negative 8.667, or you should see this as negative 8 2/3 as well. And the last part, part C, we're looking for when it's equal to 12. So again, we're going to take that derivative. These become a little tedious and a little mundane, but I'm sure you can get through them here. So we go ahead and set this equal to 0 by subtracting 12 over. 2x squared plus 2x minus 24 is going to equal 0. I can factor out a 2 again. That's kind of nice. Gives me some smaller numbers to work with anyway, huh? So here we got what? X plus a 4 and an x minus 3 equal to 0. So we know the x values are negative 4 and 3. Well, the nice thing is I've already got my calculator set up. I've already got my table set up. So if I type in negative 4, I get 27 1/3. And if I plug in my 3, I get negative 3 out. So that gives me my 2 points that we're working with there as well. So a little long on the problem, but not too miserable. I think you guys can work on that, work through that. Oh, yes. And what about this one? Our old friends are back, aren't they? The word problem. So this is the number 54 in the book, if you want to open up the book there and follow along, or it's right here as well. As use of the internet grows, so does the number of consumers who shop online, which we see that quite extensively at this point in time, don't we? The number of online buyers as a percentage of net users is expected to be P of t equals 53t to the 0.12, where t is between 1 and 7, and where t is measured in years with t equals 1 corresponding to the beginning of 2002. How many online buyers as a percentage of net users were there at the beginning of 2007? So it would be kind of interesting if this was a little more recent, but this is the latest numbers we have. Especially this year, it would be interesting to see what that would be. So how many? That's the biggest thing I want you to see in this case here in part A, how many. To figure out how many, we're going back to the original function. We're going to go to P of t. And in this case, we went of 2007. Well, if 2002 at the beginning was t equals 1, then that makes 2003 equal to year 2. 04 was equal 3, 05 would be 4, 06 would be 5, and 07 would be year 6. So well in the range of our domain, well, within our values of our domain, I should probably say, so we don't mix up domain and range, huh? So P of 6, we're going to plug in our 6, 53 times 6 to the 0.12, or the 1200ths. We can definitely use our calculator on these. I wouldn't expect you to take 6 to that exponent. And then we're going to multiply that by 53, and we end up with 65,713. All right. And that's going to be the number of the percentage of online buyers as a net users. So we expect 65.713% of net users to be online buyers as well. That's for how many, part A. Very important we see how many. And B is asking us how fast was the number of online buyers as a percentage of net users changing at the beginning of 2007. Here, I want you to notice the words, now we're looking at how fast. Well, what does fast mean? Well, how fast is a velocity? So we want to know the velocity of, or kind of the velocity of this function. How do we find the velocity? The velocity is, yay, the derivative. So we're going to find the derivative. I guess we're in variable of t in this case, aren't we? So we're going to find the derivative in terms here, so 53t to the 0.12. How do we find that derivative? We're going to take that 1200ths, and we're going to multiply it by 53. Again, pull out that calculator. We end up with a 6 and 3600ths t. We're going to decrease that exponent by 1. So we got 1200ths minus a 1, and that gives us a negative 8800ths. And now we want to know at the beginning of 2007. So again, if 2002 was year 1, 2007 is going to be year 6. So we have p prime of 6 gives us 6 3600ths times 6 to the negative 8800ths. So we can go ahead and type that into our calculator. Again, I wouldn't expect you to know that. I don't know how to do that necessarily. I guess we could figure something out with it, couldn't we? Negative 0.8800ths. So we get 1.314. And that is how fast it's changing. Well, we need some numbers there, don't we? This is going to be a percent per, and then we have a time. So in this case, it is in years. So we're increasing at 1.314% per year. I guess we don't need years, just year. And that gives us how fast this is going to change. Remember, how fast is going to have a units on it. It's going to be a rate. So whatever we're talking about in our problem, generally per a time period. And that gives you kind of an example of where we would see this out there in the real world. Good luck.